All right, so my name is Jan, and this is on work that I did together with Johannes sitting over there, which is a library we call Spray, which is a way for us to explore fun and interesting ways to implement reduction operations in OpenMP. And so, on this slide, I'm going to do a quick recap. If you've used reduction operations in OpenMP, and if you've sort of looked at the standard in any detail, you will know that the default way of doing reductions in OpenMP is for each thread to create its own private instance of the reduction variable, then perform the reduction locally, and then at the very end there's some sort of implementation-defined way of combining these thread local instances into the overall result. Now that is okay if you are talking about scalar variables, but it can be pretty bad if you're talking about array reductions, where if the array is large, then each thread will have its own private copy of that array. And we find in scientific applications that very often what we would like to do is something we call a sparse array reduction. So every thread will only really increment selected elements in that array, and it's just extremely wasteful for every thread to allocate memory for itself, initialize everything with the neutral element, and then reduce all of these elements that are mostly zero anyway. And for that reason, reductions are probably not as much used as they could be. So Spray allows us to use sparsity and give the user control over how exactly the reduction works under the hood. And the way they do that is by just sticking the reduction variable into what we call a reducer object. So here in red, we're seeing the block reduction object, which basically lazily allocates chunks of the array as needed, and doesn't allocate chunks of the array that are not needed at any time, which saves memory, but it also saves a lot of time if things are sparse enough. And we have a bunch of different reduction objects, reducer objects that, for example, use atomic updates rather than creating privatized objects, or they might, asynchronously do some updates behind the scenes without the user knowing. And all we guarantee is that eventually all the contributions are committed to the final result. Now, a question that we have gotten a lot from reviewers of our papers and also, actual or potential users is, are these reductions reproducible? And, to answer that question, we need to realize there are different kinds of reproducibility. And the one that is really the most interesting for us is that if you have the same code, but you compile it on a different system, or you run it with a different thread count, will you get exactly the same result, or will you get a slightly different result due to floating point, non-associativity of floating point summations? And for that reason, we started exploring reproducible reducer objects, which allow you to wrap your reduction variable in one of these reproducible reduction objects, and then under the hood make sure that whatever happens, you will get a bitwise exact same result on any system and with any thread count that you're using. The current implementation uses something called binned numbers, which is not something we invented ourselves. It comes from the Reproducible library, and we're just wrapping it in reducer objects. And sort of quickly giving a performance idea here, it depends very much on the system that you're on and the data size and the thread count and so on. But we're getting overheads somewhere between 50% and 300% compared to non-reproducible reductions. But you see the gray and orange lines there, which are much better and represent more like a 10% overhead. And these are things that we can do if we have the compiler help us out with instrumenting the code or giving us hints about the chunk size or the number of threads. Now, like I said, the result doesn't change at all, regardless of what happens. But of course, we can use these bits of help to, for example, know what is the chunk size going to be, or ask the compiler to only give us chunk sizes that are powers of 2, which then helps us under the hood to make smarter choices and get better performance out of it. And I'm almost out of time, so I'm just going to leave it there. We don't actually do questions now, so come and find me later if you have any questions. Thank you very much.